Welcome back. The second notebook is about the graphs of trigonometric functions. First, let's begin with the elementary trigonometric functions, sine and cosine. The simplest is the sine, and it goes like this, this one. Here is a graph of the sine function. As you can see, you have a graph that is going up and down, and the standard domain from 0 to 2 pi is highlighted in thick blue curve here. And afterward, the same pattern continues because after 2 pi, or 360 degrees turn, we come back to the original place and exactly the same thing must return, and the same pattern continues by definition. That's the nature of the angle. We saw that before. For example, if I draw this graph from 0 to, up to 6 pi, we have something like that. 8 pi, we have something like that. Do you see just going up and down the same pattern continues? Well, it should. By the way, it looks like the graph is changing a little bit, but no, that's just an illusion because we have this fixed size of the window and we're going a little bit further to the right. And consequently, the graph is being compressed a little bit, so we have an illusion that we have a change, but in fact, no, it's the same as before. So periodic behavior is associated to the sine function. The same goes to the cosine function, by the way, and here's a graph of the cosine function. Periodic behavior from 0 to 2 pi. That's normal because 2 pi is 360 degrees turn, and we just come back to the original place as before, and consequently the same behavior returns. The difference between sine and cosine are kind of like these. Sine start from 0, 0. Cosines begin from 0, 1, Sine is odd and cosine is even. Let's go over to more detail. Why do we have these kind of graphs? Well, here's a visualization how the graph of sine function come to be. Here's a visualization. In the left hand side we have a unit circle, and the angle is being visualized by the arc length of the counterclockwise direction of the arc length, starting from the initial point 1, 0 toward the terminal point x, y, which is being continued over. And in the right hand side we see a straightened version, and as we have increasing angle theta, as the arc length goes on over to the entire circumference, we see the thick blue portion of the line segment is increasing from 0 to 2 pi in the right hand side. Now, what is the function value? It is associated to the sine function. Sine is y over r. R is equal to 1 in this case. It's the unit circle you're looking at in the left hand side. So the function value is nothing more than y. In other words, the height of that red line segment, which is pretty much identical in the left hand side and right hand side, except that they move a little bit differently. That's because, well, they're coming from the same function, sine function, and sine is y over 1 in this case. By the way, if we get different standard domain, instead of going from 0 to 2 pi, if I go from 0 to negative pi to positive pi, then we are going to get a visualization kind of like this. We have the same counterclockwise motion, counterclockwise arc length, but the starting point in this case is negative 1, 0, and consequently starting angle here is negative pi, and it goes all the way up to positive pi rather than from 0 to 2 pi as we saw before. It's an alternative way to represent the same thing. Oh, by the way, if you look at from negative pi to positive pi, you can clearly see that the graph of the sine function is an odd function, symmetric with respect to the origin. Now this visualization is from 0 to 4 pi, and rotation is going on for, well, two 360-degree rotations. So we go all the way to 4 pi. And the standard domain from 0 to 2 pi is represented as solid curve. And then next we have dotted curve. In any case, we have the same behavior. And of course, I could have drawn the same thing from 0 to 6 pi or 8 pi, but the same behavior, except that the pictures get smaller and messier. You see the picture. You see how things are going, I hope. And that's how we get the graph of sine function, going up and down, generating a wave function. We call it sine wave, by the way. How about cosine function? It kind of goes like this. Similar fashion, we have a unicircle on the left hand side and then the graph of the cosine function, except that this time, instead of concentrating upon the height, we have to look at the horizontal. So you have to look at the length of the horizontal line segment on the left hand side, and that corresponds to the length of the vertical line segment in the graph in the right hand side. When this horizontal line segment goes to the right hand side of the x-axis, right hand side of the y-axis, consequently the x-coordinate is positive, then cosine is positive, and in that case, the graph of the cosine function goes above the x-axis in the right hand side. Otherwise, the graph has to go below the x-axis, and the function value is negative. In that case, x value is negative, and the point is going to the left-hand side, or second and third quadrant in the unicircle. Oh, by the way, before showing you the next rotation, how about this visualization over here? And this one takes the same cosine function from negative pi to positive pi, and the same counterclockwise rotation, but the starting point is -1, 0. So the standard domain becomes from the angle starts from negative pi to positive pi. Here you can clearly see that the graph of cosine function is even, symmetric with respect to the y-axis. Now here goes two rotations from 0 to 4 pi, and you can clearly see the periodic behavior of period 2 pi for cosine function. A little bit harder to see because you have to consider height versus horizontal. Unlike sine function, where both of them are height. In any case, this is a graph of the cosine function. It is worth remembering further properties of sine function. Sine is bouncing between -1 and +1, and that's because the height, let's go back to the first visualization here. In the left hand side, height of this red line segment is bouncing between -1 and +1 because it is bound, the terminal point is bound to the circle. It does not go beyond that. Consequently, we have the periodic behavior. And here are some interesting angles. Sine of 0 is 0, sine of pi over 2 is 1, that's when we have maximum. Sine of pi is 0 back again. Sine of 3 pi over 2 is -1, that's when we have minimum. Sine of 2 pi, we're going back to 0. What if we add or subtract 2 pi? Because this is period, you don't change anything. So sine of theta plus or minus 2 pi sine of theta. What if I add just pi? That's an interesting question. In that case, you have negative sine of theta. The reason is because, let's go back to this, adding pi simply means the same thing on the other quadrant, or as a matter of fact, the same behavior, the opposite side of the origin and the unit circle here. So when because of the symmetry, we have to have the same height in terms of magnitude, but different sign, opposite sign. In short, we have this behavior. And odd function, sine of negative theta, turns out to be negative sine of theta. And then because of the symmetry of the sine curve, sine of pi minus theta is equal to sine of theta. The last one will turn out to be rather important when you're solving trigonometric equation. And further properties include the relationship between sine and cosine here. And an easiest way to see this is to plot the graphs of sine function and cosine function together in the same viewing window. Here cosine is blue, sine is red, and then as you can see, cosine function, blue function, is just the same as sine function, except that it is shifted to the left, and it is by pi over 2. That's when a sine of pi over 2 is 1 and cosine of 0 is 1. So it is parallel shifting and the magnitude is pi over 2. And that's how we get a relationship between sine and cosine function. Sine of theta plus pi over 2 is cosine like that. And the others can be deduced from some algebraic manipulation going backward. Or, again, comparing the graphs. It's a little bit tedious and very difficult to memorize all these because they are so confusing with different signs. So what you need to do probably is to look up this table from time to time because it's nearly impossible to memorize all these. They're so confusing with different signs. And there's a pattern though. Whenever you have whenever you have pi over 2, sine and cosine are interrelated. Whenever you have plus or minus of pi, then we have change of sign. Plus or minus 2 pi, then periodic, so no change there. But then there's again a bit of a wrinkle to it. Sine of pi minus theta is sine. Again, not difficult, but confusing. Similar properties appear for cosine functions too, even adding more confusion. Again, they're easy to understand. Just look at the graph and then you can see those. I'll leave the details to you. Adding 2 pi, periodic, so same, that's easy to see. Adding pi, that's going opposite of that unit circle. So we have negative cosine, sine, cosine, they all become negative, okay. And cosine function is an even function, so we have that. And that one's a bit confusing. Cosine of pi minus theta turns out to be negative cosine. Relationship between sine and cosine, whenever you add or subtract a pi over 2 or subtract from pi over 2, we have these. Easy to see if you try to prove each individual one, but if you look at all these together, very confusing because of those signs. Nearly impossible to memorize them all. So get some patterns and then just look them up whenever things become necessary. Or you can individually deduce them whenever it becomes necessary. I don't recommend that because that's rather time consuming, but here they are.